Okay, so in this video, and for the first half of this unit, we're going to be talking about solutions. I know that we touched on solutions earlier this year, way back in the first unit, but now we're going to get more into that. All right, so a solution is a homogeneous mixture of two or more substances. And a solution has two parts to it. First, one is the substance being dissolved, and we call this the solute. And the second is the substance that's dissolving the solute, and this is the solvent. So take a second here and think about which one of these is the solute and which one is the solvent. All right, so hopefully you identified the salt going in as the solute and the water in the cup as the solvent. It's not always that it has to be solid and liquid, though. There's many types of solutions. So one type could be solid dissolved in liquid, like we saw in the image there. So that'd be like salt water or sugar water. We can dissolve a liquid into a liquid. So alcohol dissolves in water, which is why sometimes you might see on your parents' vodka that it's been like triple or double distilled, meaning that they worked really hard to get all the water out of the alcohol to improve the purity of it. And then liquid dissolved in gas, so that'd be like water vapor. So when it feels super humid, right, in the air, then that's liquid being dissolved into gas. Gases can dissolve in gas, so our atmosphere is a mix of oxygen gas, nitrogen gas, and other trace gases. And then we can have solids dissolved into a solid. And mixtures of solids are what we call alloys. So for example, we can mix copper and zinc together to get brass. We can mix iron and carbon together, sometimes also more substances as well to get steel. And then white gold is actually a mix of gold and silver. If you recall from Unit 1, while we have homogeneous mixtures, we also have heterogeneous mixtures. We have two types. One is when the particles are so large that they settle out, and these are called suspensions. And so, like if we have muddy water, right, at first it's going to look like it's pretty mixed up, but then we're going to see settling over time. So they're going to settle out of solution. The other type are when the particles are in all various sizes and they're not actually dissolved, but they're going to stay dispersed around the solution, and these are called colloids. So an example of this is milk. Milk is water mixed with proteins and sugar and fats, and they homogenate most milk, so that way it stays consistent throughout. But you might be able to get like some heavy cream, or in some places you can get milk that hasn't been homogenized, and you will see settling or cream rising to the top, and that's actually how they get that saying, cream rises to the top, is because the fattiest parts would rise to the top of milk containers. Okay, so let's talk more about these liquid-solid solutions. If we talk about if a solution is or the solute is being soluble in the solvent, that means it can dissolve. And that's what we see in this image here, right? I think this is probably coolant or antifreeze, and it's dissolving into water. It's mixing into the water. This is different than insoluble because the solute cannot dissolve into the water. So if we were to put oil into water, right, it's not going to dissolve. It's going to separate out pretty strongly. All right. So dissolution. This is actually the process of dissolving. And so what that means is that the particles of the solids are going to be pulled apart, so they're going to exist separately in the solution. And that's what we see going on here, right? We have some sort of salt, and the water ions are pulling, the water molecules are pulling the ions apart. So here we have a sodium ion being surrounded by water. Here we have a chloride ion being surrounded by water. So the water's pulling off the ions to cause this dissolution. There's some ways that we can speed this up, one of which is by stirring it. So if we stir something, right, it's going to allow the solute and solvent particles to interact more, and so therefore they're going to dissolve faster. Another way is heating it. Again, if we heat particles, right, they're going to have more kinetic energy, meaning that they're going to collide more frequently, move around more, and again, that will make it so that it's going to dissolve more quickly. We can also break it into, we can break the solid into smaller pieces. So, right, this goes back to when we were talking about reaction rates and a way to improve them, right? If we have more surface area, so more spots for it to react on, or more spots for dissolution to take place, it's going to dissolve faster. Okay. So, precipitation, this is the opposite of dissolution. So this is when the dissolved particles come back together and reform a solid. So that's what we see over here is one of these solutions has lead in it and the other solution has iodide in it, and they're dissolvable within those. So it's probably like lead nitrate and potassium iodide, and then we pour them in together, and when they mix, they form a precipitate. This is actually what you would have observed when we did the double displacement reactions in back in Unit 8. Whenever you'd see like a solid or cloudiness form, that's the precipitate forming. All right. So this brings us to saturation, because there is a limited amount that a given substance can dissolve, can be dissolved into a solvent. So, right, if we put too much cereal or too much sugar in a cereal, it's just going to pile on the bottom, which makes for very tasty milk in the end, but is one, not healthy, but right, but it's that, therefore it's not dissolving into the solution. So, a saturated solution that's going to contain the maximum amount of the dissolved solute, so no more can be dissolved. An unsaturated solution means that it can still dissolve more solute. So one way to test it is to keep adding some in until it starts to pile on the bottom, and at that point it's saturated. If it keeps dissolving, then it's unsaturated. The way we quantify this is solubility. So solubility is the amount of a solute that can be dissolved in a given amount of solvent. So solubility is going to depend on the identity of both the solute and the solvent. Oops. So like sodium chloride is really soluble in water, but oil isn't. Or nail polish isn't soluble in water, but it dissolves easily in acetone. So that's why we use acetone in nail polish remover, because it will dissolve the nail polish. Solubility is also going to depend on temperature. Now, typically, the warmer solvents can dissolve more substance, but there are a few exceptions. So just as a note within this class, we're going to talk mostly about solubility in water. So water is going to be our solvent most of the time, but it is good to know that there are other types of solvents out there, but we're going to primarily focus on water. Okay, so let's take a look at the solubility chart, because this is going to allow us to know what the solubility is for different compounds at a given temperature. So the y-axis here, the grams of solute per 100 grams of solvent, what this is referencing is if we have 100 grams of water, this is, we would go out, so say for sodium nitrate here, at that temperature, so at 30 degrees Celsius, we're going to be able to dissolve about 95 grams of it in 100 grams of water. Now, along the x-axis here is our temperatures, as I kind of referenced before. And if we see a positive slope here, then that means that the rising temperature, as we increase temperature, we're going to be able to dissolve more. All right. So let's go and do some practice with these. Okay. So it just does another way to look at it, right? At 50 degrees, 50 degrees Celsius, if we were to go to the potassium chloride line, we would see that we can dissolve about 40 grams of, I'm going to highlight this, right? So what you do, right, if we're at 50 degrees, we can go out to our potassium chloride line and see that we're going to be able to dissolve about 40 grams of potassium chloride in 100 grams or 100 milliliters of water. If that's what's going to allow us to make our saturated solution. If we add any more potassium chloride, it's just going to pile up on the bottom. All right, so let's do some more practice with the solubility chart altogether. So how many grams of potassium nitrate would be dissolved in 100 grams of water at 50 degrees Celsius? Okay, so we find potassium nitrate on our sheet here. So potassium nitrate is this line here, and we're doing it at 50 degrees. So we're going to go up the 50-degree line to the potassium nitrate line, and then go out from there. And so we'd be able to dissolve about 80 grams of potassium nitrate in 100 grams of water at 50 degrees Celsius. Okay, so let's look at the next question here. You want to dissolve 50 grams of potassium chloride in 100 grams of water. What is the minimum temperature of the water needed? Okay, so we find our potassium nitrate line, or potassium chloride line, so that's right here. We're told we want to dissolve 50 grams. So we're going to go from 50 out here. Oops, I want to use the highlighter. We're going to go from 50 here to the potassium chloride line. And once we hit the potassium chloride line, we're going to drop down. So we're going to see that around 80 degrees Celsius, we would be able to start dissolving 50 grams of potassium chloride in 100 grams of water. Okay. Now we said most of the time, as we increase the temperature, we're going to increase the solubility. But there are a couple that show the opposite. So a decrease in solubility as the temperature increases. So try to identify those. All right. Hopefully you identified ammonia here as it goes down, and cesium sulfate over here. We can also see a decrease in slope there. All right, so that's it on solutions and solubility for this video. There is a worksheet for you to do practicing these solubility charts some more.